This is Babitha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering College. Today I am going to discuss about the load line analysis of the bipolar junction transistor. So while coming to the contents, here I am going to discuss about what is meant by load line analysis and how we can able to draw the load line analysis on the characteristics of bipolar junction transistor. And next, I'm going to discuss about the operating point that is useful for faithful amplification of the given transistor. So first of all, we will see what is meant by load line analysis. So the load line analysis of the transistor is nothing but for the given value of collector to emitter voltage, what is the collector current we are getting. So that indicates the DC load line or load line of the transistor. So this particular load line we can draw for the DC supplies as well as we can also draw for the AC input signals. That is nothing but if we take the DC load line, here we are not required any AC input signal. So by using the biasing voltages itself, we can able to get the VCE and IC values so that we can able to draw the load line on the input characteristics or else on the output characteristics. But in the case of AC load line, along with the biasing voltages, that is forward bias to the emitter base junction and reverse bias to the collector base junction, generally we will use for the active region of the transistor. So along with that biasing voltages, we can also provide the AC signal to the amplifier. So the combination of this AC signal as well as biasing voltages will provide the required VCE voltage as well as IC current to make the operating point of the transistor or of the given transistor, or else we can able to draw the AC load line for the given input signal. So from this we can say for the DC analysis or DC load line we require only biasing voltages, and for AC load line along with the biasing voltages we require the input signal, AC input signal also. So while coming to the DC load line, so to draw the DC load line of a transistor, I am considering the common emitter configuration of the transistor. Common emitter configuration is nothing but here emitter terminal is acts like a common terminal between the base and collector of the transistor. That indicates the common emitter amplifier. So once we are telling that it has the amplifier means we have to operate the transistor in the active region of operation. Generally, transistor will operate in cutoff region, saturation region, as well as active region. But in order to operate as an amplifier, we need to provide the biasing conditions in the form of active region for the transistor. That is nothing but to make the transistor to operate in the active region of uh, operation, we have to give the forward bias to the input junction, that is base to emitter junction, and reverse bias to the collector to emitter junction in the case of common emitter configuration. So for that purpose only, we are connecting here it is, this is the base, this is the collector, and this is the emitter terminal of the amplifier. So here I am taking the NPN transistor. So here it is N, here it is P, and here it is again N type of materials. So input junction is nothing but base to emitter junction here. Output junction is nothing but collector to emitter junction in the case of common emitter configuration. So here transistor is a two-port network. So that's why it is having two ports, input port and output port. In the case of diode, we are having the single junction, so that we are having only single port in the case of PN junction diode so that we can able to get only the voltage versus current characteristics in the case of diode. But in the case of transistor, because of it is two-port device, we are having two types of characteristics. Those are input characteristics as well as output characteristics. So while drawing the input characteristics, always we need to take the input parameters of the amplifier, that may be in any configuration, common emitter or common collector or common base configurations. Okay. So for that, I am considering the input port, that is this side. This input port should be forward biased. So here base terminal is the P type of material, base region is the P type of material. So to make it as forward bias, I need to connect the positive terminal of the battery to this base terminal. So that's why the positive terminal of the battery will be connected to base terminal here. And similarly, emitter terminal is the negative type of region, that is nothing but N type of semiconductor material. So for this, we need to provide the negative terminal of the battery. So we connected the negative terminal of the battery to the emitter region here, so that we can say this base emitter junction is forward bias now. This base emitter junction is forward bias. And similarly, we have to make the output junction as reverse biased here. So to make output junction as reverse bias, I need to take, or I need to consider collector and emitter terminals of the output port here. So here our collector terminal is the N type of semiconductor material. Okay. So for this N type of material, we are connecting the positive terminal of the battery here. And for the emitter terminal, negative terminal of the battery, we are connecting here. That is nothing but we are providing the opposite polarity to the material here, so that we can say this output port is reverse biased. So once we are providing the forward bias to input port and the reverse bias to output port, the amplifier will operate in the active region. So once the amplifier is, or the transistor is operating in the active region, means it will provide the faithful amplification. Okay, so to draw the DC load line, we are applying the KVL to the circuit here. That is, once we apply the KVL, what we will get? Here it is VCC, the supply voltage, minus IC into RC, the drop across the collector resistance. IC into RC minus VC, the output voltage of the common emitter amplifier, that is equal to 0. So here I am taking VCE equal to VCC minus IC RC. So to draw the load line, we require, here it is VCE voltage as well as IC current. So how we can find the VCE voltage as well as IC current from this particular equation? So once, to get the VC and IC values, here if we observe this particular equation, here VCC value is fixed as well as the collector resistance value is fixed. Once we are designing the amplifier itself, we will choose these particular values. This is VCC is the supply voltage, that is fixed, and the collector resistance value also fixed. So the only VCE and IC parameters are varying here. So we need to calculate the two parameters. Okay. So to find VCE, I am taking IC equal to 0 in equation 1. Okay. What we will get here, once IC equal to 0 here, means what we will get, VCE is equal to VCC. Okay. And similarly, to find the collector current, we need to give VCE as 0 in equation 1. So in this case, once VC equal to 0 means we will get IC equal to VCC by RC. So these two particular collector to emitter voltage as well as collector current are the points of DC load line. So once we place these particular points on the characteristics of common emitter amplifier, we will get the DC load line that we will see in the next slide. That one is this. See, this VC versus IC indicates the output characteristics of the common emitter amplifier. So to draw the output characteristics, we have to take the output voltage VCE versus the output current IC. So while drawing this particular output characteristics, we have to maintain the input current as constant value. We have to make input current as some constant value here. That is nothing but to draw the output characteristics. First of all, we have to keep input voltage as some constant value, some 10 microamperes or 20 microamperes, something. We have to fix that IB value. Then we have to vary this VCE voltage. Then we will get the corresponding change in the collector current, IC. Okay, so if we do like that, we will get this particular type of characteristics for different values of base current. We will get different values of collector current. Okay, so here if we see the output current equation of this common emitter amplifier, that is IC equal to beta IB plus IC DU. So if you see this particular equation, this IC is independent of VC, independent of VCE voltage. That is nothing but the output current is independent of VCE here. So this is depending upon the base current only. Why? Because this ICU value is very less. So we can neglect this particular value. So IC equal to beta IB. Okay. So once the IB value is increasing means obviously the IC value will also increase here. So that's why for different values of IB, the current is increasing here. So here IB4 is greater than IB3 and this one should be greater than IB2 and this one should be greater than IB1 and this one should be greater than IB. So that is nothing but we are increasing the base current. Accordingly, we are getting the increment in the collector current. So that indicates the output characteristics of the common emitter amplifier. So on this output characteristics, now we are drawing the DC load line. Already we got the DC load line points or coordinates. Those are VC equal to VCC and IC equal to VCC by RC. So that values we need to indicate on the x-axis as well as y-axis of the output characteristics of common emitter amplifier. So here our VCE value is VCC. So this one we are indicating here, and similarly IC value we got here it as VCC by RC. That one we indicated here. So if we draw these two, if we join these 2 points, this particular line indicates the DC load line of the amplifier. Okay, this indicates the DC load line of the amplifier. And similarly, we can also draw the AC load line. I have already mentioned in the case of DC load line, we didn't apply any input signal for the CE amplifier. Just we provide the biasing for the input port as well as the output port. Then we got the DC load line. But to draw the AC load line along with the biasing voltages, we need to provide the AC signal as the input so that we will get the AC load line. So the procedure is same here. Again, we need to find the voltage equation, then find the VCE voltage as well as IC voltage from that equation. Then we can able to draw the AC load line. So the next thing here it is, after drawing the load line, we need to find the operating point of the amplifier. So actually, what is the basic need of the operating point? First, we have to know that. So once we fix the proper operating point for any amplifier so that it can able to amplify the signal properly, that is nothing but without any variations or without any clipping of the signal, it will provide the amplification. So that is the requirement of the operating point for any amplifier. So how we can calculate this operating point? So here operating point is nothing but those are the values of collector current as well as VC voltage when no signal is applied to the amplifier. That particular point we can call it as the operating point or Q point of the transistor. Okay, so generally this operating point should lie in the active region of the transistor. Why? Because here suppose I am taking the output characteristics of the CE amplifier, VCE versus IC. We got the characteristics like this. For different values of IB, we got different IC values. Okay, so we will draw the DC load line also by using the above processor. That is, here it is VCC and here it is VCC by RC. So here suppose my operating point is here. Suppose my operating point is here means we will get the amplified signal. We will get the total amplified or fully amplified signal here. Like this. Suppose my operating point is lying here, suppose. In this case, what will happen? The sum of or some amount of signal may clipped off here, or else if I choose here means, so in this case some amount of signal may clipped off here. So because of that reason, the operating point should lie in the active region of the transistor. So this particular region is the cutoff region and this particular region is the saturation region, and below middle of this cutoff and saturation region is the active region. So once we fix the operating point in the active region so that we can able to get the proper amplified signal across the output. So because of that reason, we need to fix the operating point properly in the active region, not in the cutoff or in the saturation regions. And so while coming to this operating point, we are having two types of operating points. Why? Because I have already mentioned in the case of transistor, we are having two characteristics, input characteristic as well as output characteristics. So from the input characteristics, we can able to find the input operating point, and from the output characteristics, we can able to find the output operating point. Okay, so to find the input operating point, again I am considering the common emitter amplifier only, same previous circuit, and I have given biasing to operate the transistor in active region. Why always we are operating the transistor in the active region means the basic application of the amplifier or basic requirement of the transistor is providing the amplification. Even though it is useful for the switching operation, but most of the times we will use the transistor for amplification purpose. So because of that reason, we are operating the transistor in the active region. So to find the input operating point, I am applying KVL to the input loop. So if I apply KVL to the input loop, I will get here it as VBB minus IBRB. Here one resistor should be there. It is drop across the resistor is IBRB, and this voltage is VB. The voltage between the base and emitter terminals is VB. So VBB minus IBRB minus VB equal to 0. So again, to find the operating point, that is IB and VBE. Why I am taking IB and VBE means in the input characteristics of the amplifier or transistor, we are having input voltage as well as input current. So here VBE is the input voltage, IB is the input current in the case of common emitter configuration. So that's why I wanted to find the IB and VBE values. So to find the IB value, what we have to do here it is, if we observe here, the value of RB resistance is fixed and the VBB, the supply voltage, is also fixed here. The only VBE and IB values are varying here. That's why we are going to find the particular varying values. Okay, to find IB, I am substituting VBE equal to 0 in equation 1. So if we make it as 0, we will get IB equal to VBB by R. So that is one of the operating point in the input characteristics. And similarly, if we make IB equal to 0 in equation 1, then we will get VB equal to VB. So this is the second point of the operating point. So P1 is nothing but 0 comma VBB by RB, that is nothing but 0 comma current. And here it is, point 2 is voltage comma 0. That is nothing but operating point is the combination of voltage and current. That may be input or output. So this is the operating point we got, VBB comma VBB RB, that is nothing but input voltage and input current. Okay, so this input voltage as well as input current we are indicating on the input characteristics of the amplifier here. So before going to that, how we have to draw the input characteristics of the amplifier, we have to see. So to draw the input characteristics, we have to take the input voltage versus input current, that is VB versus IB. While drawing this, the output voltage should be constant. That is nothing but this is VC, this is some constant value. We can take it as some 1 volt, 2 volts or anything. Okay, that is nothing but we have to fix the output voltage as some constant value first. Then we need to vary the VB voltage. Then we will get the corresponding change in the IB current. So that indicates the input characteristics of the transistor. If we draw that, we will get like this. This is the input characteristics. Why the characteristics are starting from here, not from horizon, means after the cut-in voltage only we will get the response. That is 0.3 volts for the germanium type of transistors and 0.7 volts for silicon type of transistors. And after getting the input characteristics, then we need to indicate the operating point for that characteristics. So we have already calculated VB equal to VBB and IB equal to VBB by R. So if we indicate that value, VB equal to VBB and IB equal to VB by R. These are the 2 points. If we join the 2 points, we will get the load line. And once where that particular load line is crossing the input characteristics of the transistor, that particular point we are calling it as operating point, or we can also call it as Q point. So this is the input operating point of the common emitter amplifier. And similarly, we can also find the output operating point. Here the procedure is similar to the input operating point only, but we are indicating the operating point on the output characteristics instead of input characteristics here. So to find the output operating point, I am applying KVL to the output loop or output port. Okay, so once we apply the KVL to the output port, we will get here it as VCC minus drop across collector resistance, that is ICRC, and this particular voltage VCE is equal to 0. I am taking it as my first equation. And to find the operating point or Q point, we need to find VCE comma IC. Those are the output voltage as well as output current of the amplifier. So to find the collector current IC, I am putting VC equal to 0 in equation 1. Why we are doing like this means, again here VCC as well as RC values are fixed. Okay, so once VC equal to 0 here means we will get here it as IC equal to VCC by RC. So this is one of the point of operating point. And next, if we substitute IC equal to 0 in first equation, then we will get it as VC equal to VCC. So this is the second quadrant of the operating point. So our Q is, our operating point is VCC comma VCC by RC. I have already mentioned how to draw the output characteristics. So after drawing the output characteristics, we have to mention these points. VCE value is VCC and IC value is VCC by RC. So if we join these 2 points, so this point we can call it as the operating point or quiescent point, and this line we can call it as the load line. So after drawing the load line, where that particular load line is crossing the characteristics of the amplifier, that indicates the operating point, and always the operating point should lie in the active region of the transistor. Then only we will get the proper or faithful amplification of the given signal. And actually once we are fixing the operating point means it should not change with any variations. But here the collector current value is varying. Why? Because if we take the operating point, we are having the VCE and IC. Almost always we are getting VCE equal to VCC. VCC is nothing but our supply voltage or biasing voltage. So this value is fixed, this one is not changing. So always the IC value will only change. Once the IC value is varying means the operating point will also vary here. So how this IC value is varying? Because of which parameters IC value is varying? Actually, the collector current is varying with 2 parameters here. One is, if any change in the beta, the collector current will also change here. Beta is nothing but the current amplification factor in the common emitter configuration. And we know already IC equal to beta IB. This one we got from the beta equal to IC by IB. So from this relation, we can write IC equal to beta IB. Suppose here if beta value is increasing means the collector current will also increase. If beta value is decreasing means the collector current will also decrease here. That is nothing but the collector current is depending upon the beta value here. And similarly, the collector current is also varying with the variation in temperature. For that purpose, I am considering the output equation or output current equation of the common emitter configuration, that is IC equal to beta IB plus beta plus 1 into ICBO. So in this case, this beta plus 1 into ICBO indicates the ICEO, that is the leakage or reverse saturation current in the common emitter configuration. So once the temperature is increasing means this reverse saturation current will also increase. So once this value is increasing means the overall collector current will also increase here. So the temperature is increasing means the collector current is also increasing. So from this we can say the collector current is varying due to the current amplification factor as well as temperature variation. So in order to make the operating point as stable or without any variation, we have to nullify the changes for the collector current. That is nothing but variation of beta as well as variation of temperature. We need to nullify to make the IC as stable. If we make the IC current as stable means we will get the stable operating point. So now we'll see some examples related to this DC load line as well as operating point so that we can understand easily. So for that I am taking the problem. Here it is. The figure is showing that a silicon transistor. So for the silicon transistor, VBE voltage is 0.7 volts here. Okay, and with beta equal to 100. The current amplification factor is 100. Is biased by base resistor method. That is nothing but fixed biasing method. For this, draw the DC load line. Draw the DC load line and determine the operating point. That is nothing but Q point. And what is the stability factor? So we need to find these three parameters from the given circuit. They already mentioned the supply voltage and the base resistance value and the collector resistance value. So to find this, to find the load line as well as operating point, we have to apply the KVL for the given circuit to the input side. Okay. So here these are the given values. Supply voltage is 6 volts, base resistance is 530 kilo ohms and the collector resistance is 2 kilo ohms. So to draw the DC load line, from the figure we can write VCC minus ICRC minus VCE is equal to 0. Here this is VCC and this IC into RC and this voltage is VC connected to emitter voltage. So from this we can write this equation VC equal to VCC minus ICRC. So to draw the DC load line we require VCE value as well as IC value. So to find the VCE value I am putting IC equal to 0 in the first equation. Once we keep IC equal to 0 here means we will get VC equal to VCC and that VCC value is 6 volts here. So VC equal to 6 volts. So this indicates the first coordinate, first point of the DC load line, that is 6 volts. And to find the IC value, we have to substitute VC equal to 0 in the first equation. Then we will get IC equal to VCC by RC. Here VCC value is 6 volts and the RC value is 2 kilo ohms. Then we will get it as 3 milliamps. So VC equal to 6 volts, IC equal to 3 milliamps. So by using this we can draw the load line. See, VC equal to 6 volts, IC equal to 3 milliamps. Okay, indicate on the characteristics so that if you join these 2 points, that indicates the load line. Okay, we have calculated the points of load line. We have drawn the load line. Next, we need to find the operating point. So to find the operating point, once we consider it as the silicon transistor, so VBE value is 0.7 volts. So from the figure, again we can write it as, from the input side of the circuit, we can write it as IB into RB plus VB equal to VCC. So from this we can write the IB equal to VCC minus VBE by RB. So here we have all the values. Supply voltage is 6 volts, VBE voltage is 0.7 volts and base resistance value is given as 530 kilo ohms. After substituting all these values, we will get it as base current as 10 microamperes. Always the base current value is very less compared to the collector current and emitter current. And always we will get collector and emitter currents in milliamperes and base current in microamperes, because base is very lightly doped as well as very thin region. And next, we have to calculate the collector current as well as collector to emitter voltage to make the operating point or to find the operating point. So the collector current IC equal to beta IB. So beta value is 100. Generally beta value will take here it as 100. The maximum value of beta is 100 and the maximum value of alpha is 0.99. This is in the common base configuration. This is in the common emitter configuration. So beta value will lie from 45 to 100 range and alpha value will lie from 0.95 to 0.99. Almost it is equal to 1. So here beta is 100 and IB is 10 into 10 power minus 6. So we will get it as 1000 microamperes, that is in liquids. It has 1 milliamperes. And similarly, we have to find the collector to emitter voltage VCE. That one we can get from the first equation, that is VCC minus ICRC. We have calculated already this one. So these values are VCC is 6 minus IC value is 1 milliamp into RC value is 2 kilo ohms. So we will get it as 4 volts. So the operating point values are 4 volts and 1 milliamps. So this we have to indicate on the characteristics. Okay, if we indicate on the characteristics, VC equal to 4 volts and IC equal to 1 milliamp. So if we take the lines like this towards the DC load line, where it is touching the DC load line, that indicates the operating point. So operating point is 4, 1 milliamperes. 4 volts, 1 milliamperes for the given problem. And the stability factor for the fixed bias circuit is beta plus 1. This one we know already. So beta value is 100 plus 1, 101. So the stability factor is very high in the case of fixed bias circuit. So the stability is very less. That is nothing but there is much variation in the collector current in the case of fixed bias circuit, and the operating point will also vary more in the case of fixed bias circuit. So that's why most of the cases we will not use the fixed bias circuit for the amplification purpose. Generally for the gain control circuits we will use this fixed biasing circuit of the transistor. And next problem is design based resistor bias circuit, that is nothing but again fixed bias circuit for a C amplifier. For the operating point is, they already given the operating point, that is VC equal to 8 volts, IC equal to 2 milliamps. Okay, and you are supplied with a fixed 15 volts DC, that is nothing but VCC equal to 15 volts, and a silicon transistor. Once it is silicon transistor means VB equal to 0.6 volts. If it is germanium means 0.3 volts. With beta equal to 100, current amplification factor. Take base emitter voltage as 0.6 volts. Calculate also the value of load resistance that would be employed. How much load resistance required for this particular amplifier we need to find. So for that, here these are the given values. VCC equal to 15 volts, beta equal to 100, VB equal to 0.6 volts, and we need to find the RC and RB values. So for that, I am applying KVL to the outer loop of the circuit, that is VCC minus ICRC minus VC equal to 0. So from that we can write this VCC equal to VC plus ICRC. So we have all the values except RC here. If we substitute that all the values, we will get RC as 3.5 kiloohms. Okay, and next IB value. If you find the IB value, here we have the IC value as well as beta value. If you substitute the two values, IB value is 0.02 milliamperes. And to find the RB value, here we require RB as well as RC values. RC we have calculated already, and the RB value from this equation, it is VCC minus VBE by RB. So we got this equation from the input side. If you apply the KVL to the input side, we will get it as VCC minus IB into RB minus VBE equal to 0. The supply voltage drop across the base resistance and this input voltage. So from that, RB equal to 15 minus 0.6 divided by 0.02 milliamperes. That we are getting here it as 720 kiloohms. So these two are the required resistances of the given circuit. So while coming to the next problem. So here the temperature value is increasing from 25 degrees to 75 degrees for the given circuit. Okay, and if the beta is 100 at 25 degrees Celsius and 150 at 75 degrees Celsius, they already mentioned two temperatures. At 25 degrees how much beta is there, and at 75 degrees how much beta is there. Determine the percentage changing Q point values. We have already mentioned the Q point is the values of VCE and IC. If the IC value is varying, means the Q point will also vary here. So here beta value is varying, means definitely IC value will also vary. Why? Because IC equal to beta IB. So once the beta is changing, means how much IC value is varying, asking in the question. Change in the Q point values, VCE and IC over this temperature range. Neglect any changes in VBE and the effects of any leakage currents. So here first we need to find the IB value. From that we can find the IC value. So this IC value we need to find for both the temperatures at 25 degrees Celsius as well as at 75 degrees Celsius. So to find IB, I am applying KVL to the input side. I will get it as VCC minus IB RB. VCC minus IB into RB minus this base to emitter voltage is equal to 0. So from this we can write IB equal to VCC minus VBE by RB. So substitute all the values so that we will get it as 0.113 milliamperes. And again IC equal to beta into IB. After substituting that, we will get it as 11.3 milliamperes. And similarly VCE voltage. So to find the VCE voltage, we need to apply the KVL to the output port or output loop. That is, we will get it as VCC minus drop across collector resistor. That is IC into RC minus this voltage between collector and emitter terminals, that is equal to 0. So from this we can write VC equal to VCC minus ICRC. After substituting all the values, we will get it as 5.67 volts. So the operating point at 25 degrees Celsius is 5.67 volts, 11.3 milliamperes. So once the temperature is changing from 25 degrees to 75 degrees, how much variation is there in the operating point? We will see now. So for that, again same procedure we need to repeat at 75 degrees Celsius. Here the thing is, the beta value will change here. Okay, IB value is same. Why? Because in the IB equation we don't have any beta value. So that's why IB value is same. And IC value will change here. Why? Because beta is changed from 100 to 150 here. So we got IC as 17 milliamperes. And similarly, VC equal to 2.48 volts. Why? Because if the IC is changing, means VC will also change. Why? Because in the VC equation we have IC here. So how much change in the IC? To find that, we have to take the collector current at 75 degrees Celsius minus collector current at 25 degrees Celsius divided by collector current at 25 degrees Celsius. So after substituting all that values, we will get it as 50%. So once the temperature is changing from 25 degrees to 75 degrees, the collector current is increasing 50%. Okay, so once the IC is changing means VCE will also change. So VCE is decreasing by minus 56.3%. And the next problem is for the emitter bias circuit. This is another kind of biasing circuit, emitter biasing circuit. Shown in figure, find the emitter current, collector current, VC voltage and VCE for beta equal to 85 and VBE value given it as 0.7 volts. So to find the IC value, apply KVL here, so that we will get it as IC equal to VE minus VBE by RE plus RB by VT. So after substituting all these values, we will get it as 1.73 milliamperes. And similarly, to find the VC value, here it is. So to find VC value, this particular point, this supply voltage minus drop across this RC resistance, that is VCC minus IC RC. If you substitute the values, we will get it as 11.9 volts. And similarly, VE voltage. So to find the VE voltage, that is minus VEE plus drop across emitter resistance, that is IARE. So minus VEE plus IARE. We will get it as minus 2.7 volts. But we require here it is VCE voltage. To find VCE voltage, we have to take it as VC minus V. That is 11.9 minus of minus 2.7 volts. We will get it as 14.6 volts. So the operating point here it is 14.6 volts, comma 1.73 milliamperes. So the asked values are IC, VC and VC as well as operating point. And the next one is determine how much Q point will change over a temperature range where beta increases from 85 to 100 and VB is decreased from 0.7 to 0.6 volts for the given circuit. So to find that when beta equal to 85 and VB equal to 0.7 volts, the same values we have used in the previous problem also. So that's why I am taking IC as well as VCE, same values 1.73 as well as 14.6. Okay, these values for beta equal to 100 and VB equal to 0.6. Okay, and to find the IC, we are taking VE minus VBE divided by RE plus RB by beta. After substituting all the values, we will get it as 1.76 milliamperes. And similarly, we need to find the VC value, that is VCC minus ICRC. We will get it as 11.7 volts. And next, find the VE value, that is minus VE plus IERE. After substituting the values, we will get it as minus 2.4 volts. So here we got the IC value. To find the VC value, we calculated VC and VE. So VC is nothing but the subtraction of VC and VE. We will get it as 14.1 volt. So next we need to find the percentage change in the collector current. That is 1.76 minus 1.73. This value as well as this value divided by 1.73. That is 1.7% increment in the collector current. And similarly, we need to find the change in the collector to emitter voltage. So the 14.1 volt we got from this particular given circuit and 14.6 we got at beta equal to 100. After substituting both the values, we will get it as minus 3.5%. So it is decremental. So IC is increasing, VC is decreasing here once the beta is varying. So these are the different problems related to the load line as well as operating point. Once IC value is changing, how the operating point is varying, we discussed here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.